No, but you look like you did, but then like. Boy, didn't you? Boy, came from. Bag rugged as the you just gotta pull up one day and like something. You have a phone. How long? Every time I go to the food, you're like, what's your we're at
Okay, wait, I don't have to. Okay. Okay, we're going.
On Friday, isn't it?
Quick. And then he had a whole. I don't know. I think it might interfere with the. I'm pretty sure we don't.
Someone who's met like.
Oh, boy.
I think it's like $1.
I don't even know. Usually all wanting to just fill in.
There's one.
Okay, guys.
Right, page 1. We're going to talk about alternating series error bound, and we can only right now we're going to see other variations of this later, but this is going to be the easier of the Lagrange error bound that we're going to see later. So right now, understand that we can only do this for alternating series. So we must be looking at a converging alternating series for this to happen. So what is our goal here? Our goal is we want to find a safe boundary of the accuracy of our partial sum. So we know that when we do a partial sum, we're only going to get getting an approximation of the actual sum, right? The more terms that we add together, the closer we are to our actual sum. But we're not really concerned about what the actual sum is. We're more concerned about what is a safe upper bound? What is a safe estimation of the accuracy of our approximation? So we're trying to find a safe estimation of the accuracy of our partial sum. Again, we're not so concerned about what the actual sum is. I mean, for us, we only are concerned about finding the actual sum for very specific series, right? If it's a converging geometric series, then we can find the sum. If it's a telescoping series, we can find the sum. But for other series, we're only concerned about can we decide if it's converging or diverging? And if it's converging, we may be able to do how accurate or what is a safe estimate, or what is a safe estimation of our accuracy. So let's fill out this table below. Right. So my alternating series would be, if I plug in 1, I would get 1. If I plug in 2, I would get -1 to the 1 plus 1, which will be plug in 1. Sorry. Okay. Sorry. If I start with 1, I get a positive alternator. But if I plug in 2, I'll get a negative because it's raised to the third power. So it'd be -1/2. And then the third term, n for 3 and for n, I will get +1/3. Okay. -1/4. These are just the individual terms here. We haven't added them up yet. So 1/5, -1/6, 1/7, -1/8. The decimal version will just make it easier for us to make some comparisons later. So I'm just going to write the decimal versions of the terms above. Okay. All this is just to demonstrate and show you what this is doing. So we're just using this data for demonstration purposes. Now let's find these partial sums. So we're going to find S sub 1. We're going to find S sub 2, S sub 3, S sub 4. So S sub 1 would just be 1 minus 1/2. Oh, sorry, just 1, right? Just 1. S sub 2 would just be adding the first 2 terms of the series. So 1 minus 1/2 is 1/2. S sub 3 would be adding the first 3 terms. And the idea is that the more partial sums that we add together, the better our approximation should be, right? We're getting closer and closer towards the sum, supposedly. And we know that this is the case because we are looking at a converging alternating series, right? It fulfills the condition. This is an alternating harmonic series. Okay, I'm just going to fill these numbers in for us. We can just copy this. Now, decimal versions, just for comparison purposes. So 1.5. So I want us to plot these partial sums, and I want you to see what's happening with these partial sums as we move through. So the initial partial sum is going to be up here at 1. Then the next partial sum is going to jump down to 0.5. And the next partial sum is going to jump back up to 0.833. And then back down to 0.583. What do you notice? What's happening to these partial sums here? It's kind of jumping, it's getting closer and closer towards the sum, but it just keeps on hovering above and below that sum that we're expecting, right? So we're getting closer and closer, but we're always kind of over, we're always going past the destination, right? It's always, but it's getting closer every time, right? So 0.583 followed by 0.783, then followed by 0.616, then followed by 0.759, then followed by 0.634, so the actual sum, again, we're not concerned about what the actual sum is. I just wanted for demonstration purposes, the actual sum is actually going to be natural log of 2, which is 0.6931, which is right around here. So the more partial sums that we accumulate, the closer we are to that actual sum, right? But it's just going to keep jumping above and below this 0.6931 until it gets closer and closer and closer until eventually, if we were to add up infinite terms, we should be able to get to the sum, but our purpose is not trying to find the sum. Now let's talk about how far we are off of the actual sum. Just again, this is just for demonstration purposes. This is a long way of showing you what the rule is doing. So I'm going to do all the work for us. I'm just going to be subtracting my actual sum with my partial sum. I just want to show you what the actual error is and what do you expect the error to do as we move on, right? It should be closer to 0, right? Our errors should be better and better. Our approximation should be better and better. Our accuracy is also better. So if I do natural log of 2 minus 1, that will give me the error, which is, it's already pretty close, right? Even after the first partial sum, I'm sitting at 0.3068. I'm only 0.3068 off of the actual sum. And then if I do a partial sum, if I do natural log of 2 minus s sub 2, that'll give me 0.193, and then 0.14, and then 0.1098. Okay. Our accuracy is getting better and better. So what's the whole point of this? The whole point of this is, can we get to a quick approximation as to how accurate our partial sum is? And here's the trick. Let's say I wanted to find out how accurate my partial sum is for this s of 3. Okay, I just want to pick out a random number here. Okay. I want to do a quick approximation in terms of, can I just gather some quick data in terms of how accurate this approximation is? And we know this approximation, 0.833, is only off by 0.14, right? Again, normally we don't know that because normally we don't know what the actual sum is. But you see how this is the actual error. Well, the way that we can get a quick approximation for the error or the accuracy of this third partial sum is we can simply look at the first term, the next term in that sequence. The next term in that sequence, 0.25, or the absolute value of 0.25, is going to be a safe boundary for the actual error. So this 0.25 is obviously not as accurate as 0.14, but it's decent, right? And so that's what this alternating error series bound is saying, is that if I want to find the accuracy of my partial sum, I can simply look at the next term, and that next term will give me a safe estimation of the accuracy of my partial sum. So that's all we're doing. We don't really care about how accurate our partial sum is. We just want to get a quick approximation of our accuracy without having to do a whole lot of work. Okay. So this is a quick, convenient way to assess the accuracy of our partial sum approximation. So let's go down to our formula here. So this alternating series error bound says if you have an alternating series that converges, so that's important. It's got to be a alternating series. It's got to be a one that converges. We can approximate the sum of the series. So absolute value of S minus S sub n. Again, a lot of times we don't know what the sum is. We just know the partial sum. But the actual error of that partial sum is going to be some remainder R sub n. Again, we're not going to know what this value is, but we know that this is going to be less than or equal to my A sub n plus 1. So my first unused term is a safe worst case scenario of the accuracy of my partial sum. So my error bound is the next unused term of the partial sum. So if I want to assess the accuracy of my S sub 5 partial sum, then I can just look at the what? Look at A sub 6. Yep. If I want to find a quick accuracy assessment of my partial sum of my partial sum S sub 10, I can just look at the 11th term. Okay, so we don't have to worry about but how accurate really is that next is this error bound? We don't have to worry about that. We just have to worry. We just know that it's a pretty good approximation, and it's a quick way to get our approximation without having to do a whole lot of work. Just look at the first unused term. But it's got to be an alternating series, and it's got to be a converging series for us to be able to do this this assessment. Okay, let's just do 2 problems, and then we can go back and work on our quiz review. So let me just do 2 quick examples of this. So this is a calculator active problem. So we're just going to do problems 3 and 4. We'll do the easier ones, and then we'll save the more involved ones for later. So page 2. So in your calculator, we're going to go to Math 0. So it says approximate an interval of the sum of the series using the alternating series error bound for the first 5 terms. So let's just start off by using the calculator to have it give us S sub 5. So I want to find the sum of the first 5 terms. So my 5th partial sum. You're going to use x's. Oh, wait. Let's show up as x's. Let's see. So math 0. Let's see if I can get it easier. I'll start at x equals 1, and I'll go to 5. So I want to find the first 5 terms of my partial sum. -1 to the x plus 1 times, sorry again. Sorry, I keep messing up here. Okay. Sorry, it's hard to see here. So I entered in from 1 to 5, and I'm using x's. I'm not using n's. So math 0, that'll give me my summation notation. X from 1 to 5, -1 to the x plus 1 times 4 over x squared. I get that fractional value. I'm converting to a decimal. So 3.354, that is my partial sum, my S sub 5. And I want to know how accurate is this partial sum? What's the worst case scenario in terms of the accuracy of this partial sum? So I can simply look at which term to get a safe accuracy approximation here. Yep, look at the sixth term. So I'm going to find a sub 6. And it's the absolute value of a sub 6. Okay, again, our error bound, we're always just looking at the positive value of it. So if I want to find the sixth term, just plug 6 in for n. I can ignore the -1 to n plus 1. It's just going to keep alternating between -1 and 1. So 4 over 6 squared is equal to 1/9, which is 0.111 repeating. So it's not bad. I mean, even though the fifth partial sum, we're only off by at most 0.111. So we don't know the actual sum, but we do know that the actual sum, our actual sum must be 3.354, give or take 0.111. So just based off of the fact that we're using the fifth partial sum, our sum has to be somewhere between 3.465 repeating and 3.243 repeating. What if we were doing this with the sixth partial sum or the 10th partial sum or the 50th partial sum? What would you expect this interval to do? Yeah, it gets tighter and tighter, right? The more partial sum that we use, the better our accuracy, and then we can expect that interval to tighten to get closer, right? Again, we don't have to worry about, wait, but how accurate is this really? That's not something that we have to worry about. We just have to be able to find a safe upper bound and give it an interval of values based off of the limited data that we have. All right, let's try one more and then we can move on to our quiz. Any questions here? All right, so let f of x equals. So this summation will end up giving you 1 minus x squared over 3 factorial plus x to the 4th or 5 factorial minus x to the 6 over 7 factorial. So what if I were to do f of 1? If I were to find f of 1, I would just insert it in for all the x's. So let me just write out the first few terms of f of 1. So f of 1 will be roughly equal to 1 minus 1 squared over 3 factorial plus 1 to the 4th over 5 factorial minus 1 to the 6th over 7 factorial plus ... It says show that 1 minus 3 factorial. So that's just the first two terms. What can I call this? This is my what? S sub 2, right? Show that my S sub 2 has an error that is less than 0.01. Right? So if I want to find a safe approximation for my S sub 2, I can simply look at what? My A sub 3, right? My A sub 3 will give me a safe worst case scenario of the accuracy of my S sub 2. So it just wants to know, can I show that this is less than 0.01? If this is less than 0.01, then I know that my error is going to be less than this, right? Because this is my worst case scenario. So I'm going to write it in the definition form that we established on the previous page. S minus S sub 2, the actual error of my partial sum is guaranteed to be less than or equal to the absolute value of A sub 3. Right? I know this is true. It can't be any worse than what my first unused term is giving me. And A sub 3 is 1 over 5 factorial. And 1 over 5 factorial is 1 over 120. And 1 over 120 is less than 1 over 100 because 0.01 is 1 over 100. So we know that our worst case scenario, we're off by no more than 1 over 120, which is safely better than 0.01. So the big takeaway of this section is simply that if I have an alternating converging series, I can always do a quick approximation of my partial sum by looking at the first unused term in my series. And that's basically it. Okay, let's go to our quiz review. Any questions from 6 through 10 that you want me to go over with you? Oh, yeah. Okay. Number 9, which page? 4. Page 3, this one. So this is page 3, question about page 3, number 9. So which of the following series converge? This first series, I can just merge the ends together and it comes out the end of 3 halves, and that's a key series that converges. This is a geometric series that converges. And here, if I go through use substitution, I can show that my natural log of ln of b is going to end up in the numerator. Infinity minus a real number is going to diverge. So this is going to be a use substitution showing diversion. So only 1 and 2 will convert. There's a specific part that you have to. Right. Okay, what about anything from page 6 through 10? Okay, which It's only, sorry, yeah, this one is only asking for absolute convergence. So absolute convergence means that I'm stripping away my alternator and I'm just looking at the absolute value. And if that absolute value diverges, then it's considered absolutely divergent. Yeah. So if it's absolute converging, it has to be able to converge without the alternator. And we know that a harmonic series is not going to be able to achieve convergence unless it has the help of a alternating series. So we know that this is a conditional convergence, but it's not absolute convergence. But these are absolutely convergent because if I were to strip away the alternator, they can still stand on their own. They can still converge on their own. All right, so can we spend the next 5-10 minutes just making progress on worksheet 3, page 11? Yeah. Which page? Number 30. So here's ratio test. Ratio test says this. Find the limit as n approaches infinity of a sub n plus 1 over a sub n, and see if that result will give you less than 1, equal to 1, or greater than 1. If it's less than 1, it'll converge. If it's equal to 1, it's inconclusive. If it's greater than 1, it's divergent. So this is my a sub n. And because of the absolute value, we can ignore the alternator. The alternator has no say, or we can, it's just a negative positive here. So my a sub n plus 1 just means replace every n with n plus 1. So I have 1 over n plus 1 factorial. Dividing by a sub n is same thing as multiplying by the reciprocal of a sub n. So I'm just going to take that 1 over n factorial and flip it and make it n factorial over 1, just to save a step. And now let's just see what can we do to clean this up so we can cancel some stuff out. So n factorial, I'm going to let it stay because I know this will decrease down to n factorial. So n plus 1 times n factorial. I just want to find a matching pair so I can cancel out. So then what's the limit of this? 1 over n plus 1. 0. And 0 is less than 1. And since 0 is less than 1, we know this series converges. Less than 1 is probably. Yeah, less than 1 is converging. Greater than 1 is divergent. Equal to 1 is inconclusive. We should be doing a different test if we get equals to 1. Yeah. And the reason that we call this absolute convergence is because it doesn't need the alternator to converge. It can converge all on its own. If something needs the alternator to converge, then we call that a conditional convergence, which is that this is conditionally convergent. The alternator is the numerator. Yeah. Or you can write it this way. Yeah, the alternator is just the -1 to the n. It can be -1 to the n, it can be -1 to the n plus 1. I mean, technically that could be in the denominator as well. Doesn't it's usually written in the numerator, but it could be in the denominator. We just ignore it. Yes, you can ignore with ratio test. Because of the absolute value. The absolute value will just force everything to be positive anyway.
do after.
Mhm.
That's what.
Yeah.
There's a lot more integral testing.
Yeah, so anything that looks like U substitutions would be a good integral test. I mean, we did that here. That's good. These are two separate problems, so I can treat them separately.
Oh, but I didn't think I should have done that.
Mhm.
Because if one conditional diverges, then you choose.
It's the one that diverges. If one converges to one, the other goes to infinity. It doesn't matter that this is converging. There's no way I can get it converging to actually infinity. Right, exactly. Right. Yeah. This one is this nth term
Yeah,
first.
I don't know why I didn't do this.
Yeah, nth term first. Unless it's like you can obviously tell that's geometric or P series.
Here, I just didn't tell them.
Yeah, these are integral tests because these are all your substitution problems. It doesn't fit into geometric series, it fits G series. I mean, down the road we can use limit comparison test with the P series, but for now you're kind of forced into integral tests. Yeah, I mean you can take another version of this to.
Like, I understand what I did wrong on all of these. I'm just embarrassed. But
I mean, the important thing is that you understand it enough to do with the quiz of this way.
like write down what's.
And then we can do this the recovery next one or something.
I did my so on the cover, I guess it's recovery. Is it all like the same kind of questions? Okay, so like if there's a question in the unit that didn't show up on like the test that I took, it won't be in the recovery. Okay. And I wanted to ask, why you can't use pieces and have to
Because P series would be something that is more like this. I can do P series there, but as soon as I add 3 or subtract 3, it turns into something, it's in the same family, but then I gotta do limit comparison steps, more direct comparison steps. And that's the way you can use it. So you kind of have to force, on this next quiz, you can use limit comparison test. But because this quiz, it forces these tests, the only one that you can use.
Okay.
But yes, in the big picture, you could use limit comparison tests with P series and make the same conclusion.
Okay, thank you.